right, so after section 4.1 with anti-differentiation, we're going to go to section 4.2. Now 4.2 is a kind of a strange little section right after anti-differentiation, but it's very important to get us to section 4.3, so kind of bear with us. Now 4.2 has a little bit of a review element in it for us because we've covered so much of this in pre-AP. Because the first part of section 4.2 deals with our summation notation or sigma notation, depending upon how you want to refer to it. And that's that big capital sigma for Greek letters. Now, it has a counter. This is where we're going to start. This is our pattern. And this is our stopping point. Okay, now we're going to learn a little bit of a different name for this in chapter 8. We're going to know that this is called our sequence. And when we did these last year, the variable, that little counter there, wherever you see an I here, that's what you're going to replace. You're going to replace with these numbers. Now the increments we go by are ones. So the first one we'll plug in is 1. The second number would be 2. Then 3, then 4, 5, all the way up to 6. 6 is where we're going to stop because that's where it tells us to stop. This is called summation notation because you are adding all of these individual terms together. So you should get a total of 21. Now when we do these, we need to make sure that we're writing out the members or the elements in each one of these sequences as well as the value. Now we will be able to use our calculator on this, but very often we don't get to use the calculator and we need to see the pattern forming so that when they want us to, we can go back from this sequence of terms back into our summation notation. So just to kind of let us know what number 2 would look like, we're going to put 0 in for our I, then 1 in, then 2, then 3, and so on. And we stop at 5. Okay? And we add all those together and we get 21 again. Weird. Okay, on our last one, we're going to put 1 in for our case, so 1 over 1 plus 1, and then 2 over 2 plus 1, and then 3 over 3 plus 1, 4 over 4 plus 1, and we stop. Okay, so make sure you're keeping track of where you start and where you stop, and then of course adding all those together. Now you can also write these a little bit more simplified if you would like. So if you don't want to write 1 over 1 plus 1, I'll need to see the 1/2, blah blah blah, all the way to 4/5. And then of course I will need to see the sum. Sometimes your calculator will put it back as a fraction, sometimes it won't. Remember, all decimals have to be accurate to 3 decimal places. So when you're doing these in class, I'm going to require that you give me that sequence written out and that sum. Okay. Now, this is how we did it. Just to refresh your memory, last year we discussed how to do it on the calculator. So here it's in your notes, so I'd like you to try to do it on your own. If you need additional assistance, then come see me individually and we'll make sure that you know how to use that on your calculator. But once again, very rarely do they let us use our calculator, so we need to know both ways. All right, so now this is where we have to go backwards. So as you're getting the summation notation and you're writing out the sequence, it's important for you to write out that sequence so you can see how to go backwards. Because this is how you see it on the ACT. They give you a pattern and they want you to find out what that sigma notation would be, what the pattern actually is. So I always start off with my sigma. I choose a counter, whatever. I'm going to choose a starting point. Now, if some of them are fractions and some of them aren't, remember, make them all into fractions. That way I can see that I've written too high. Okay, so let me take her down a little bit. Oh, nice, sigma. Once again, I'm setting the bar low for you all. All right, so I can see the top is all ones, and I can see the bottom, it starts with 1, 2, 3, 4, 5. It goes up by 1, so that tells me this is going up to 5. This has got to be I. Whatever variable you have in the pattern position, that's what you also have to have in the counter. So always make sure these match, or it's not going to go anywhere. Okay, now number 6, we have something that is alternating. If it alternates, that means it has to have a negative being taken to a power. So on this, I notice it's 2, 4, 8, 16, 32, 64. Those are powers of 2, and then they alternate. So I'm going to put a -1, and then I'm going to put a power, and I'm going to see where I want to start and see if it's going to alternate properly. I know this is 2 to the 1 power, 2 to the 2nd, to the 3rd, to the 4th, to the 5th, to the 6th. So I'm going to start at 1 and end at 6. If I put that 1 in there for the I, I'm going to have 2 to the 1. I'm going to have -1 to the 1. So my first term is going to be -2. I needed it to be a +2. So I'm just going to come up here and add 1 or subtract 1. This is not the only way you can do this. A lot of people like to combo the problem and put the negative on the inside, maybe do something like this, and then to make sure it has the correct, gotta have your -2 in parentheses so that it will alternate. And then that didn't start off right, so they put another negative out there. So there are lots of different ways that you can do this. Please don't think that the one that I'm giving you is the only answer. All right, so, okay, this one you've got 9, 16, 25, 36, 49, 64. Those look like squares. I'm going to change it up a little bit. So I'm going to use K. So these are squares, so K squared. That's 3 squared all the way to 8 squared. Okay. Okay. So now on number 8, ooh, this one's kind of tricky. I'm going to stick with my K's. The bottom, those are even. So 2K, that makes sure I'm even. Odd, I'm going to do 2K, that makes sure it's even, and then I'm either going to add 1 or subtract 1. That's going to make sure that we're odd. Well, this is 2, that's 1, 4, 3, 6, 5, so it looks like we're subtracting 1. We are starting with K equals 1 because 2 times 1 is 2. 2 times 1 minus 1 is 1. We're going all the way to 1, 2, 3. Looks like there we go. Okay. I don't know if you can pick up on this or not in the video, but the band is practicing behind us here. So if you hear some noise, that's what you got going. Alrighty, now, like I said, 4.2 is kind of a hodgepodge of things. In section 4.2, we are also going to talk about the area under a curve. Okay, the area under a curve is a total amount. Okay, now what we're going to do is we are going to estimate this area under the curve. So I want us to look at a nice pretty curve here. Okay, when we're estimating the area under this curve, we don't know yet how to find the exact area under this curve. We know how to find the area of circles and squares and rectangles and so forth, but not anything that has these nice little curves. So what we're going to do is we are going to use the only geometry we know. So we are going to approximate the area under a curve using rectangles. We're using rectangles because those are easy. The formula for the area of a rectangle is base times height. Okay, the change in x, that's going to be our base. The height is going to be our y value. When you look at your little graph here, the base, that's the change in x. The height is your y value. Okay, makes sense. And then we're going to be adding these up. Now, in order to make sure that this is as easy as possible, we are going to make sure that the bases of our rectangles are exactly the same. So we're going to use this little formula to help us out. Delta x is going to be b minus a divided by n. So when they ask us, they're going to ask us to find the area under a curve from a to b. That's where they get this a and this b. using this many rectangles. That's going to be the n. So they're going to give us all this information and we are going to put it all together. Okay, so looking at this right here, let's say they told us we wanted to estimate the area from 1 to 9 and they want us to use 4 rectangles. Okay, so that means we've got from 1 to 9. If we're going to do 4 rectangles, we're going to go from 1, oopsie, I don't even know what happened there. Okay, so we're going to go make a line here. So from here to here, and then we're going to go from here to here, because if we're going from 1 to 9, we know that they're going to go by 2s. And then from 9. Okay, so looking back at that, I did my delta x was going to be 9 minus 1 divided by 4, so that was 2. So starting at 1, because that's your first endpoint, so from 1, if I add 2, that'll get me to 3, add 2, that'll get me to 5, add 2, that'll get me to 7, plus 2 gets me to 9. Now up here, there are lots of different sums we could use. And we're talking about Riemann sums here. That's what it's called. So we can do left sums, we can do right sums, we can do lower sums, which is also called inscribed, upper sums, which is called circumscribed, midpoint sums, and trapezoidal sums. Now, when they're talking about left sums, right sums, we don't even have to graph it in order to get this value. Because if it's left sum, that means looking at your rectangles, I have rectangle 1, rectangle 2, rectangle 3, and rectangle 4. When I'm looking at a left sum, that means when I'm looking at this rectangle here, it's not a rectangle yet. I've got this weird, funky little top going here. Left sum means I want you to take the left endpoint and draw straight across. This now will be the rectangle that we look at in this interval. Okay, left sum, you take the left endpoint and you draw straight across. So this is the rectangle that's going to represent this interval. Left sum, straight over, I'm a little over there, and then left sum straight over. Okay. Now, we're going to be using these 4 rectangles to estimate the area under the curve. Now, it's an approximation because you can see there's some area that is not being used at all. I didn't even count that area or this area, and then I overshot that area. So that's why it's an estimation. Some are going to be a little high, some are going to be a little low. Okay? But left sum is you're going by that left endpoint. Okay, now let's look at what a right sum might look like. Let's do that in blue. Okay, so looking at the same rectangle with the base going from 1 to 3, right sum means I would start at the right endpoint and make my rectangle out and down. Same thing, rectangle 2, I'm at the right side, so I'm going to be going up here and down. Same thing here, right side of that rectangle straight across, right side straight across. So you can see that one of them, left sum, if it's an under approximation, right sum's probably going to be over, okay? And vice versa, okay? So right sum, left sum, those are the ones that we use the most because you do not have to graph it to know which one is the right endpoint, which one's the left endpoint. Now, when I go back to the other, and let's say they want me to find the lower sum and the upper sum. Now, when I'm finding the upper sum and the lower sum, I really do have to have this graphed. Because if you're doing lower, that means you need to see which side of the rectangle is lower, because you are always going to go on the lower side. Lower sum will always be a low approximation. Okay. Upper sum, you're always using the upper endpoint. That upper sum will always be an over approximation because you're going high every single time. And every single time you'll have to know what the graph looks like in order to get that done. Okay. Now here are your formulas for left sum, right sums. They've got formulas, but logically you can figure them out. Trapezoidal is a good approximation because it's the average of the left and an average of the left and the right sum. Because it's that average, if one's high and one's low, then the trapezoidal is a little bit better, okay? It's kind of like the baby bear. Too hot, too cold, just right. Okay, so we're going to find the approximation, and we're actually going to do left sum. So please change that and right sum, okay? That way we don't have to draw the picture. Okay, now when you don't have to draw the picture, all we need are those points. We need the delta x, because that's how wide our rectangle is, and we need our y value, because that's how high our rectangle is. Looking at our little information here, delta x is going to equal 9 minus 1 divided by 4, because 1 and 9 are your endpoints. 4 is how many rectangles. So once again, we're going by 2's. So start with your left endpoint, add 2, add 2, add 2, and add 2. You should have one number more than the number of rectangles you're working with. Now to find the height of those points, you're going to plug 1 in for all your x's. So 1 over 1, 1 over 3, 1 over 5, 1 over 7, and 1 over 9. So when we're finding the left sum, we are going to use these rectangles. Now, the base of every rectangle is 2, and we're going to use the left. So left is going to use the left endpoint, everybody but the right endpoint. So I'm going to do 2 times 1 plus 2 times 1/3 plus 2 times 1/5 plus 2 times 1/7. Okay, now what we've done here is we've just done 1 rectangle, 2, 3, 4. So each one of those rectangles, we're finding the area of that rectangle, and then we're adding them all up. This will give us an approximation of that area under the curve. So if you put those in your calculator, nice, handy little calculator, you're going to end up with 400. Nope, you're going to end up with 352 over 105. Okay, now for the right sum, we're going to star those with blue. You're going to start with the right endpoint, and you're going to use everybody but the left. Now, if you'll notice, each one of these rectangles has the same base, and we meant to do that. So instead of writing 2 times 1, 2 times 1/3, 2 times 1/5, 2 times 1/7, we're going to do 2 times the quantity, and then we're going to just put those heights in there. Remember, you're not using the left endpoint if you are finding a right sum. So my right sum is going to be 496 over 315. And you'll notice that one's high, one's low. If we wanted to find the trapezoidal, we'd take the average of these two answers and divide by 2. Okay, let us do another. Okay. Once again, we're going to do left and right. This time, our delta x is going to be 2 minus 1 divided by 4. So delta x turns out to be 1/4. When we're making our little table of points so that we'll know what our y values are, we're going to start with our left endpoint, and we're going to add 1/4. and add 1/4, add 1/4, and add 1/4. You should end up exactly on that right endpoint. And once again, if your number of rectangles is 4, you should have 5 points. And I do. I'm going to put 1 up into the original equation here for my x's so that I can find the y coordinate. So these guys right here, you're plugging in here to find those. Okay, so that's going to give us 15 over 16, 3 over 4, 7 over 16, whoopsie, and then 0. Okay, so right sum. Remember, the width of every rectangle is 1/4. Now we just need the height. It's the right sum, so I'm going to start here. Use everybody but that left endpoint. So 15/16 plus 3/4 plus 7/16 plus 0. Now I know you're probably thinking, why do you have the 0 there? I like to write the 0 so that I know I've done 4 rectangles. 1, 2, 3, 4. When I multiply all of that together, I get 17 over 32. Now I'm going to do the left sum. I'm going to use the left endpoint and everybody but the right. Width of each one of my rectangles is still 1/4, so 1 plus 15 over 16 plus 3 over 4 plus 7 over 16. That's going to give me a total of 25 over 32. Okay, so right sum's a little low, left sum's a little high. Trapezoidal would be just right. And remember, the trapezoidal sum, you would take 17/32 plus 25 over 32, divide that answer by 2, and that would give us our just right value. Okay. Okay, the last one we're going to do deals with our trig function. So just real quick, our delta x should be pi over 4. Oops, forgot my x there. Okay, when I'm looking at these values, the sign of 0, let me write our little table out. The sign of 0 is 0. The sign of pi over 4 is square root of 2 over 2. I'm using pi over 2. That's going to give me 1. 3 pi over 4. That gives me square root of 2 over 2. And then the sign of pi is 0. So start at your first endpoint and then just keep adding pi over 2 until you get to your second endpoint. If n is 4, you should have 5 points. Okay, so on this one, I just want you to find the trapezoidal. Well, if they only give you the trapezoidal to do, you can use the trapezoidal formula. You are always more than welcome to find the left and the right sums and then average them together. Okay, but if you want to use the formula as is, you're taking your delta x divided by 2. You're taking one of each endpoint, but then 2 times the insides. Because when you're averaging them together, okay, they both have these guys in the middle, but the left sum only uses the left endpoint, the right sum only uses the right. So if we were finding the trapezoidal, we get pi over 8 times 2 plus 2 square root of 2, reduce. So pi over 4 times 1 plus square root of 2, that's about as low as you're going to go. End your parentheses there. Okay. So that's as pretty as our answer is going to be. All right, I'll see you in class.